Hello everyone, welcome to my YouTube channel. My name is Shobit Awasthi and today I am going to explain you the Dining Philosophers Problem. Let's take a brief overview of the Dining Philosophers Problem and later on we will understand in deep and detailed study of the problem with its solution. So, the Dining Philosopher Problem is a key synchronization challenge in computer science. It illustrates resource allocation complexities in concurrent systems. Let's understand concurrency in operating systems. Here are the key aspects and benefits of concurrency in OS. Let's try to understand the definition of concurrency. Concurrency allows multiple processes to be executed simultaneously, enhancing system performance. What is its impact on system architecture? It is effective concurrency management significantly influence system architecture and performance. So what is parallelism and what is multitasking? Parallelism executes processes at the same time, while multitasking switches among multiple processes. What is the importance of synchronization? Synchronization mechanisms prevent race conditions and ensure safe access to shared resources. What are concurrency models? Different models like actor and message passing help manage concurrent processes effectively. Performance benefits of concurrency are systems with good concurrency can handle higher loads and improve overall throughput. User experience enhancement. Efficient concurrency directly improves user experience by reducing response times. Relevance in multi-core environments. Concurrency is crucial for modern multi-core processors to utilize resources efficiently. Challenges of deadlock and starvation. So with synchronization comes challenges. So first of all, we will try to understand what is the definition of deadlock. Deadlock is a situation where processes are unable to proceed due to mutual resource waiting. And what is starvation definition? A condition where a process is perpetually denied necessarily resources for execution. Now, how to manage resources? We should properly allocate and manage the resources to avoid deadlocks and starvation. For this, we use mitigation strategies that are techniques like deadlock detection and avoidance to enhance system performance. Also, we use Banker's algorithm, which is a deadlock avoidance strategy, allocating resources based on maximum needs. Solution to the dining philosopher's problem are resource ordering to prevent deadlock. Imposing an order on fork usage prevents circular wait conditions, allowing philosophers to eat without conflict. Waiter controlled access to forks. A waiter limits the number of philosophers eating simultaneously, reducing the chances of deadlock. Dynamic resource allocation algorithms. Utilizing algorithms like wait die and won't wait ensures that processes do not wait indefinitely for resources. So, what are semaphores and mutex? Let's try to understand the definition of semaphore. A semaphore is a signaling mechanism controlling access to resources by maintaining a counter. What is the definition of mutex? Mutex allows only one thread to access a resource at a time, ensuring exclusive access. Semaphore use cases. Semaphore are beneficial in scenarios with a fixed number of identical resource available. Mutex use cases. Mutex are ideal for protecting critical sections of code from concurrent access issues. Avoiding deadlocks. Effective use of semaphores and mutexes is crucial to avoid deadlocks in concurrent systems. How to prevent starvation? Proper implementation of these concepts helps prevent starvation in resource allocation. Efficiency of systems. Using semaphores and mutexes leads to improved system stability and performance. Visualizing resource allocation graphs. Resource allocation graphs (RAGs) help visualize resources. RAGs identify potential deadlocks by highlighting cycles. Analyzing RAGs can enhance system reliability. RAGs improve insights into safe and unsafe states. Real-world applications of Dining Philosophers Problem are given here. Database management systems. The Dining Philosopher Problem influences strategies to prevent deadlocks in DBMS, ensuring data integrity. In distributed system, concepts help resolve resource contention, ensuring fair access among processes in distributed environments. In multi-threaded programming, principles from the program guide algorithms for efficient resource allocation in multi-threaded application. In optimizing system performance, insights gained aid in optimizing performance and reliability across various computing environments. Operating systems design. It impacts the design of OS for effective concurrency control, managing multiple processes and efficiently. Case studies in concurrent programming. It gives insights on concurrency challenges and solution. First is web server. Web server application is multi-threaded web server. We can have multi-threaded web server. Its strategy is to allocate resources based on dining philosophers, and the impact on web servers is that it reduced deadlock occurrence by 40%, improved server responsiveness. In database system, the application is on database management. The strategy is about semaphore based resource management, and the impact is it decreases contention and increases the throughput by 25%. Future concurrency in OS. Advanced synchronization techniques. Research in log-free algorithms and weight-free data structures to minimize contention and enhance performance. Machine learning integration. Use of machine learning to predict and prevent deadlocks and resource contention dynamically. Complex system management. Growing need of robust frameworks to manage concurrency in multi-core and distributed systems. Evolving developer paradigms. Developer adapting to new approaches for efficient and fair resource allocation. High performance systems. The ongoing exploration of concurrency drives development of high performance systems for complex applications. So let's conclude this overview and call action on dining philosophers problems with a detail. Let's embrace the principles of concurrency management to enhance system reliability and performance while staying informed on best practices in operating systems. So let's start with the detailed discussion of the dining philosophers problem. So basically, Dining Philosopher's Problem is a classic concurrency problem that illustrates the challenges in resource allocation and potential for deadlock and starvation in concurrent systems. Proposed by Esgar W. Jastra in 1965, this problem serves as a fundamental example for understanding and resolving concurrency issues in operating systems and distributed computing. It is a crucial concept for many computer scientists. The setup is simple but profound. Five philosophers sit around a table, each needing two forks to eat. The challenge lies in coordinating access to these shared resources to avoid conflicts and ensure that each philosopher can eat eventually. So problem setup is given five philosophers seated around a circular table. In front of them is a plate of delicious spaghetti. But to enjoy it, each philosopher requires two forks. But between each philosophers is a single fork, resulting in total of five forks available for the group. Philosophers. Five philosophers are sitting around a circular table. They alternate between thinking and eating. Forks. Five forks are placed between each philosopher. Each philosopher needs two forks to eat spaghetti. These philosophers spend their time alternating between thinking and eating. When a philosopher gets hungry, the attempt to pick up the fork on either side of them. However, because the forks are shared, not all philosophers can eat simultaneously. The challenge is to design a system that allows the philosophers to eat without creating conflicts or deadlocks. So, the problem is deadlock. The core issue arises when each philosopher attempts to pick up the fork to their left. If all philosophers perform this action simultaneously, they will each be holding one fork and waiting for the fork on their right, which is currently held by their neighbor. Pick up the pick up the left fork. Each philosopher grabs the fork on their left and then wait for the right fork. All philosophers are now waiting for the fork on their right. What's the deadlock here? No philosopher can proceed, resulting in standstill. All philosophers are blocked indefinitely. This situation leads to deadlock state where no philosopher can start eating because each is blocked, waiting for the other to release a fork. In this state, no progress is possible and system is effectively frozen. Conditions for deadlock. Deadlock occurs when four conditions are met simultaneously. These conditions are fundamentally to understanding and preventing deadlocks in concurrent systems. First one is mutual exclusion. For non-shareable resources only, one philosopher can use a fork at a time. Second is hold and wait. Philosophers hold one fork while waiting for another. They do not release the fork they already have. Third is no preemption. Forks cannot be forcibly taken away from the philosophers. Resources can be preempted. Resources cannot be preempted. Fourth is circular wait. A circular chain of philosophers exists, each waiting for the next one to release a fork. This creates a closed loop of dependencies. If any of these four conditions is not met, deadlock cannot occur. Solutions to the dining philosopher problem typically focuses on breaking one or more of these conditions. Solution number one: resource hierarchy. One effective solution involves imposing an order on the forks, numbering them from 1 to 5. This establishes a resource hierarchy that prevents the circular wait condition. First is the number of forks. Assign a unique number of a number to each fork, 1 to 5. Then pick lower number first. Each philosopher picks up the lower numbered fork first. Third, release in reverse order. Philosopher release forks in reverse order after eating. By following this approach, the circular wait condition is broken and not all philosophers will be waiting for a higher numbered fork. This avoids the deadlock situation, allowing philosophers to eat in coordinated manner. Solution number 2 is the arbitrator. Another approach involves introducing an arbitrator, such as a waiter, who manages the allocation of forks. This centralized control can prevent deadlock by ensuring that philosophers only eat when both forks are available. Philosophers request both forks from the arbitrator. Arbitrator verifies that both forks are available. Arbitrator then allows the philosopher to eat if both forks are available. The arbitrator limits concurrency by allowing only one philosopher to eat at a time, but effectively prevents deadlock. While it may reduce overall system efficiency, it guarantees progress and avoids the starvation of in any individual philosopher. Third solution is breaking hold and wait. To avoid deadlock, the hold and wait condition can be broken by requiring a philosopher to pick up forks only if both are available. If fork is not immediately available, the philosopher must release the fork first and wait before retrying. The philosopher should check availability if both forks are available before picking them up. If both forks are available, the philosopher picks them up. If the second fork is not available, the philosopher releases the first fork also. This approach requires the ability to check fork availability and before attempting to pick them up by preventing philosophers from holding one fork while waiting for another. The hold and wait condition is broken and deadlock is avoided. Summary to the dining philosopher problem is a valuable example for understanding concurrency challenges and the conditions that can lead to deadlock. What is concurrency? Illustrates challenges in managing shared resources in concurrent systems. Deadlock it arises from mutual exclusion, hold and wait, no preemption, and circular wait. Solutions are involve resource ordering, arbitration, or breaking hold and wait conditions. Understanding these concepts is crucial for designing robust and efficient concurrent systems. The problem solution offer insights into strategies for managing shared resources, preventing deadlocks, and ensuring progress in concurrent environments.